inviting me at this colloquium. I'm going to face the problem of crack evolution, and I will show some aspects that are concerned with computation aspects using variational approach. Standard linear fraction mechanics, linear elastic fraction mechanics, is based on the Griffith criterion. That it is basically a stability criterion that allows to find the condition for a crack to extend by an already existing crack extends by an infinitesimal increment. Computationally, this is quite complicated to face. Usually there have been suggested many ways for approximating the problem, and there is also some physical problem with this model. This slide I borrowed from experiments made in Parma by Professor Carfagni, and this the onset of a crack in a very brittle glass. And you can observe that at the tip of the crack it is damaged. So it seems that even in an extremely brittle material like glass, crack is never a completely elastic phenomenon. It's always accompanied by by some damage in the material. That suggests a justification for trying to use another kind of approach to fracture. It is the cohesive model. The cohesive model was proposed by Barenblatt and is extensively used in computational mechanics. The main motivation for this work are that if we want to study the evolution of a fracture in solids, we need the three ingredients. A way of inserting the discontinuity in the displacement field, some activation criterion, and an algorithm for detecting a fracture path. Now, so mathematically the problem was so this would be the outline. I will skip to describe the outline, and mathematically the problem was set on sound basis in the late 90s, thanks to a series of works, starting with the one in 98 by Van Fort and Marigot, and then many others. Professor Piero contributed with several contribute, and they showed, for instance, that the proposal was to use a variational formulation where you have to find the minimum, or say the stability condition for a functional, which is the sum of the internal energy of the continuum, the potential energy of the loads, plus another term which is a fraction energy. Many papers were written. First, the authors considered Griffith energy, which is thus a constant multiplied by the surface of the crack. later other attempts were done in using Barenblatt approach to fracture, which can be seen as a regularization of Griffith energy. Now, my point was how can I introduce this kind of mathematical framework within a numerical scheme. When we make finite or say discrete approximation, we start usually with this functional, which is Uva-Shizu functional. It's a three-field functional where we have the first line are all the energy involved in the continuum, and then there are the Lagrange multiplier that enforce the compatibility conditions. The dissipation is usually taken in this way. In this form, we can model many phenomena like plasticity, damage, and so on. So the idea is, if we just extend this functional, introducing energies for the discontinuity on the fracture and a compatibility condition for the discontinuity, introducing an internal variable would be the jump of the displacements. So we can try to follow the same kind of reasoning and right? Okay. And the stationarity conditions of this function, I'll give all the equation of the problem. With the arrow, I have pointed to the new conditions that are pertinent to the problem of fracture. In a similar way, I can introduce the dissipation functional for the surface. This is just a sketch that is simply in a 1D case illustrates how is defined the dissipation functional. It is actually the support functional of a domain, an admissible domain for the tractions, for the traction on the surface. In a more general setting, it would be something like that, and this form has been given by Frankfurt and Marigot, and they show that it is the most general form of the activation condition for any interface. Differently from the original work, I introduced also internal variables in order to model with an additional internal variable to model the softening of the surface. There are also these are two different choices for this internal variable that give rise to either a linear or exponential, whatever decay we want. The fraction energy is obtained as the sum of the dissipation function and the internal energy of the interface, which is the internal energy of the internal variables. More general cases can also be considered, like this one, in order to model eventually unloading. Otherwise, would be could be unrealistic. What happens is that if you insert all this in the functional I showed before, the jump of the discontinuity, all the internal variables can be condensed at the local level. So so that you end up with a problem with this only set on the displacement variables. And next step is to introduce a parameterization. So this all the integral will be written in a parametric domain. J will be the Jacobian of the transformation, and then some regularization, because the dissipation I've shown is not differentiable at the origin, so we choose the classical regularization with the Lagrange multiplier. And this would be these are the equations we have to solve. The first are the equilibrium equation, and we get the displacements. The others are local equation giving the traction on the refracture, internal variables, and the Lagrange multiplier, which are related to the entity of the jump. Now, let's go back to the variational formulation. The variational formulation is equivalent to the stability condition that says that the functional I've shown before is the smallest one among all the functional obtained on the displacement and on the shape of the crack. This problem is very similar to the problem of shape optimization. The idea is that including a crack is like changing the shape of the domain. Shape that can be changed introducing a deformation of the domain itself, on a part of the domain actually, not all of the domain. And in this way, we can find the rate of variation of the functional with the change of the domain using the shape derivative, which is a classical tool in shape optimization. Shape derivative actually is defined in the first line. It's like this is just a derivative, and it is known that if the functional the function of pi is the total potential energy, we have that the shape derivative is given by this defined integral where E is the Eshelby tensor. Since the Eshelby tensor is divergence free, we can also calculate the same quantity using the flux of the Eshelby tensor on the boundary of the domain. That seems very appealing because typically in a crack problem the boundary domain remains the same except a small portion. However, computationally it is not very convenient because around the crack there are many, the solution shows many errors. So it's more convenient computation to use the computation on the whole domain. And that's what is done in the next slide. This is shown how the first domain, the integral, what is the form of this integral? It gives the shape derivative, and what is written is that changing the shape or change the position or the length of the crack modifies the Jacobian of the transformation in some part of the domain, and in all these integrals the variation is done on these Jacobian terms. So this is the idea. How can we do it computationally? Yeah, no, I can. Okay, I run. Okay. If you use classical finite elements, this is quite hard. If you insert a crack in a finite element context, you have to remodel the old, to reformulate the old connections. So the idea is to use isogeometric interpolation. Isogeometric interpolation is based on from spline. It was developed in Austin about 10 years ago, 15 years ago. Now it's starting to be quite widely used in computational analysis. Splines are highly continuous function. Usually they are function of degree 3, 4, but especially they are not like shape function in the classical sense. They are a partition of unity, but they are not function that are one at the nodes and so on. And they are, it's typically, if you use a spline of degree p, this spline is different from 0 in p elements of the discretization. So the idea is, if we break this function between two adjacent elements, we introduce a discontinuity. This is shown in the picture. On the left-hand side, there is on the right-hand side, there is the idea of splitting the spline between two elements. The different way of doing that is inserting nodes with high multiplicity. This is being proposed, but this requires the addition of new degrees of freedom, new nodes, and so it's less convenient. Okay. Then the additional degrees of freedom can be just with the transformation of coordinates be transformed in jumps and also the derivative of the jumps. And this would be the functions. Of course, in the 1D case, the function is at the bottom relative to a jumps in certain position for a third degree spline. In a 2D case, we have this more or less the same. These are two typical functions that one can see that there are some problem. Since the splines are very highly continuous, the discontinuity spreads a lot. It's not concentrated on the track. You see this function here. Okay, just a very simple example. This was the example, just to see that this is a beam. The position of the crack, of course, in this case is known. This is the solution. We find the minimum, of course, in the right position. This okay. Let's skip this one. This is what is obtained in the case of this one-dimensional problem, modifying the position of nodes in order to get the right position of the crack, and then that slide shows how the Jacobian that is originally constant equal to 1, I guess, or something, how it's modifying the position of the nodes. And this is the solution, which is, of course, reproduced what we expect, unless there is a problem with this problem. If you see that the pictures, the plots of the actual force, you see that we would expect a spike. So it is quite smooth because the functions are have high continuity, contrary to what happens with finite element. So in this case, we have this smooth solution. Just to see what can happen in a 2D case. This is beam, bending beam, and this is Again, this shows how modifying the path of the crack, that means modifying the position of the nodes that define the elements, how the Jacobian is modified within the domain. And in this case, we see that the modification of the, let's see, there's another picture, I guess, yes, is quite local, is around the crack. However, I said spreads in the domain. That's the reason for I said is using the computational of the shape derivative of the whole domain is usually more accurate than just trying to do it along the crack. So the conclusions, and that is just want to stress that this idea is different from what has been proposed up to now for fracture with the splines that use different methods, quite more complicated, and well, we are working on some more sound examples in order to understand the potentiality of this method.
Thanks very much.